Hi viewer, this is EasyElimu channel. I'm Vincent Kanmaya and I'll be taking you through Form 3 Mathematics. And today we are going to handle the topic of circles, chords and tangents. Welcome. Today I'm going to start with length of an arc. We shall handle it under circles. And as we know, given a circle, if that circle is divided into given angles, which we may refer to as theta, you will find that it subtends a given circumference to that circle. Let's see, for instance, for example, given this kind of a circle, let's say we have a section which is cut to give it let's call this one angle theta, and you will find out that given that angle, you can find the arc length given like AB and dimensions of theta, whereby in this circle here, having this and cut an angle of theta, we are having two arc lengths. One is of the major segment and another one is of the minor one, and you will find that this theta here will subtend this angle. Let's say the arc length AB is subtended by an angle theta at the circumference, and this arc length here is what I'm referring to as a minor arc. You will find this is a minor arc, whereby if we have a minor arc in a circle, then it will automatically rise that the remaining part of this circle is the major, this one here, which is measured by an angle of 360 minus theta. Then this one is what we shall refer to as a major arc. This arc, which is subtended from this section, if you move up to B, but using the outside direction, then that one will be major arc. And sometimes you may be asked to find the arc length, of which may be the major arc length and sometimes is the minor arc length. If you're not being told in that case, then you will be told calculate the arc length which is subtended by either, let's say, by an angle which is acute or maybe obtuse, but maybe it is a minor or a major. You will be referred by given angles. For instance, if given this one as theta, you may be given that you have an angle and a radius and be told to find the arc length, or sometimes you may be provided with the arc length which may be like this or similar to this, and be asked to find the angle if you have the radius. Or sometimes you may be given the circumference of the whole circle and the arc length and be asked to find the angle together with the radius. Thereby, having in mind all that pertains to have a circle, you can use the relationship and find the given arc length. And remember, if you want to find an arc length, you will have it that arc length is always subtended by an angle theta from the center of that circle. So if that arc length is, let's say, is subtended by an angle theta, then to find that arc length, you will take the section which is subtended over 360, which is now theta, for example, over 360, which is the total degree subtended by the circumference of a circle. Then you multiply by 2 pi r. Because remember, to find the circumference of a circle, we do take 2 pi r, but for this case, we are taking a section of that circle. So meaning that we shall take that section which is theta over 360 multiplied by 2 pi r. May it be major arc or minor arc, the formula still stands. So we shall take an example and see how we can calculate or we can solve some of the problems concerning arc, the length of an arc. And our example for today will be: find the angle subtended at the center of the circle by an arc of length 20 centimeter if the circumference of the circle is 60 centimeter. Now, for instance, for this case, we are having this one as 20 centimeter, meaning that the distance from here up to here is 20 centimeter. But the circumference of the whole circle, this 20 included, we are having the circumference as being told as 60 centimeter. So the circumference is 60 centimeter, but the arc length is 20 centimeter. Now, let's see how we can calculate first the radius. After getting the radius, then we do calculate the angle. What we shall do, we know to find the circumference of a circle is given by 2 pi r. And here we have been given the circumference is 60. So we need to find the radius. First we can make r the subject of the formula, whereby we shall divide by 2 pi, and we find that r is given by circumference over 2 pi. After getting that, then we substitute the values which are present and we find our r. So we shall say to find r is equal to, where r is the radius of that circle, then circumference we are having 60 centimeter. Now pi here, I will use pi as 3.142. So we shall have 2 multiplied by 3.142. And you find that if you calculate, you are going to have r as, r is 9.54805. So 9.54805.8. So to cut it short to, let's take to 1 decimal place or 2 decimal places, we shall have 9.55 centimeters. So we are having our r as 9.55 centimeters. So after getting r as 9.55 centimeters, then we can use that relationship where we have the arc length and we have the radius to find the angle theta. Remember, to find the angle theta or to find this arc length here, we said you take theta over 360, then you multiply by 2 pi r. Now we are having this r and we having the arc length. So we needed to find this theta. We shall replace. Now we have the radius and we have the arc length. So we shall use the relationship where 20 centimeter is equal. First, let's give the formula, and we are having the formula as to find that arc length is given by taking theta, which is the angle subtended by that arc length to the center of that circle, then we multiply by 2 pi r. And here we are having 20 centimeter as our arc length, and theta we don't have, that is what we are seeking. And then we shall multiply by 2 by 3.142 as our pi, and radius we are having as 9.55 centimeter. So with that, we are going to have our theta will be equal to 20 multiplied by 360 over 2 by 3.142 by 9.55. Let's see, what do we get theta as? Theta is equal to 119.975 degrees, of which we can give it as 119 point, or just to 1 decimal place, we shall have 120 degrees. So it shall be 120.0 degrees. So this is what we shall have theta to 1 decimal place. So we are having this angle now here as 120 degrees. That is what we find if we use the relationship between theta, radius, and the arc length. That is what we shall find. So, having understood what I have taught here, I will give you one exercise and you should use the information there and relationship and handle and see if you will find the angle. That is, two circular wires of diameter 9 cm and 12 centimeters are cut and joined to make one large circle. Find the radius of this circle. Here, we need to find the radius of the circle formed after two wires of different diameters, meaning they will have different circumferences. So after joining the circumference, you will find one larger circle. Then use the relationship and find the radius of that circle. First, you need to find the circumference of that circle with a diameter of 9 and the circumference of the other circle, which is of the wire with a diameter of 12. So after finding the two circumferences, add them together, then you will find one circumference which will be of the larger circle and use the relationship to find the radius of that circle. Let's see how we can now find chords. And with chords we know a chord in any given circle, you will find that it is a line which is straight joining 2 points on the circumference of that circle. So we shall see, for instance, having a circle and how that chord can be represented. This is the circle with the center here as O. So we shall find that if you have been told we have a chord, then that chord you may find it as here or in any direction. So if you have a straight line here joining two points on the circumference, let's say this is point A and this is point B, then if you have a straight line joining the 2 points, that is what we refer to a chord. Let's start with looking at a perpendicular bisector of a chord. That is what we shall look at, of which I'm going to look at that one. That is what I'm starting to look at. And if we are having a perpendicular bisector of a chord, so I shall extend the points which the chord joins or cuts the circumference of that circle at point A and B to the center. On joining them to the center, you will find you are going to have a triangle in that case. And that triangle, whereby the distance from that part O to A is now the radius of that circle, the same to that. And you will find that if you drop any perpendicular or another chord which will cut, that is actually the radius, to cut that line AB at point, let's say M, and give this one as O. So we are going to have OMA and B. You will find that it cuts at that point. That is a bisector of the angle, and you are finding it is cutting at M. But this still, if you extend it, you are going to find it's a radius of that circle. So having that, we can witness that from this we shall have, since this is R, that R, so meaning the two sides OB and OA, OB is equal to OA, which are the radius of the circle. So this one is radius of the circle. So let's just say radius. And having that, we can still identify that this AB is what we are having as the chord. AB is our chord. But remember, we are having this triangle OABA. So we are having a triangle OAB, which is this total triangle. And from this triangle, if a straight line is cut or bisected this angle, you will find it cuts at this point, the chord AB at point M. meaning each cut is equally, so we shall have AM equal to MB. AM equal to MB, and this one we find it by construction, whereby you bisect the angle subtending that chord at the center. So you will find it cuts it into two parts, meaning AM will be equal to MB, and that one you will find it by construction. So from that section, then we shall have two triangles here which are similar, and if this one cuts at this point, you will find that we are going to have this angle which is 90 degrees. So meaning that if you take angle AMO, it will be equal to angle OMB, and this one will be equal to 90 degrees. And if you do that, you will find that after constructing, you are going to have it as 90 degrees. But remember what? This is radius, this one is also radius, and we have found this one here is equal to this side because this bisector here cut the line into two equal parts, having AM equal to MB, and we shall have that way. But if you view it well, you're going to have this, we are going to have triangle OMA equal to triangle OMB, that is triangle OMA is equal to triangle OMB, and we can say that one is equal because this is right hand side and right angle triangle, and we are also having one of the sides equal to each other. And remember, OM of this triangle here, OM of triangle OAM is equal to OM of triangle OMB, and this one we are finding to be common line between the two of them. It is a common line. So meaning that this OM is perpendicular to perpendicular to line AB. We are finding it is perpendicular. So having that, we can say that triangle OMA and OMB are equal by right hand side rule, whereby each of them is a right angle triangle, but they are having one of the sides similar or the other one. So they are equal or similar with a rule of right hand side rule. So with that we can say we have this OM being perpendicular to AB, and since AB is our chord, then we can say that if you drop any line which is perpendicular to line AB from the center, or you drop any line from the center of that circle to cut the chord AB into two equal parts, then we shall have that line being perpendicular bisector to that chord. So it's like constructing a perpendicular bisector to the chord. So meaning that any perpendicular line drawn from the center of a circle will always bisect any chord in that circle into two equal parts. So it will be a perpendicular bisector of that chord. So that is how we see perpendicular bisector of a chord. So we shall see next on parallel chords, but before then we need to handle one of the example which will give us or the relationship which we have already seen. So we are having a chord of 12 cm long is on a circle of radius 10 cm. Find the distance of the chord from the center of the circle. A chord of 12 cm long is on a circle of radius 10 cm. Find the distance of the chord from the center of the circle. So what we are going to do here, we are being issued with some information that the chord here, we shall use what we have here. Now I've drawn the circle and I've been informed that the circle has a radius of 10 cm. So this meaning that if it is 10 centimeter and my chord is 12 centimeters, so it means this is the chord, and the radius will be the same on both sides, since the chord touches 2 points on the circumference, let's say A and B. And if that is the case, the distance from that point A or point B to the center is 10 centimeters, which is the radius of that circle. So we need to find the distance from the center of the circle to the chord. That just means the perpendicular distance from the center of the circle to that chord, which is the perpendicular bisector of that chord. So we need to find this distance here, and I shall refer to as x. If that is the case, we understand that if you drop any perpendicular from the center of the circle to cut any chord in that circle, it means it will cut it into two equal parts. So meaning this part will be equal to the other part, and that will be 12 divided by 2. You will get this part is 6 centimeters, the other one is 6 centimeters. So having that, we can use the relation of Pythagoras theorem, which you learned in Form 2 and also in Trigonometry 2, and we shall use it to find the length x. If we have 6 centimeters, whereby it has been cut into two triangles of right angle each side, whereby this triangle OB, let's say this point T, OBT, we are having it a right angle triangle the same to other, and they are similar and congruent. So we can say that we shall take one of the triangle here, and I'm taking this triangle, which I'm having this side at 10 centimeters, the lower side is 6 centimeters. I'm cutting this triangle here, and here is point O, this is T, and this is B. I need to find this side, which is x. So on finding x, we know that from Pythagoras theorem, if we are told this was A, this one B, this C, then it means if you take A squared plus B squared, you will find C squared. For that instance, the same applies to this. I will take x squared plus 6 centimeters squared. Then this one, if I do that, will give me 10 centimeters squared, because that is my hypotenuse. So meaning that if I need x squared, then I will take 10 centimeters squared minus 6 into bracket centimeter squared. And on doing that, I'm going to have this one will be 100 square centimeter minus this one is 36 square centimeter. And if I do that, if you do subtract, you are going to have 64. So if you subtract here, it's going to give you 64 centimeter square. And that is the value of x squared. So if you need only x, then it means x alone, you will have to find the square root on both sides. And on finding square root on both sides, you are going to have x as square root of 64, you will find it is 8, and square root of square centimeter, you will find it as 8 centimeters. And now, so meaning that here the distance from the center of the circle to that chord, then it is 8 centimeters. That is how we use the relationship between perpendicular bisector of a chord and the chord itself in a circle. You can solve other problems which entails the problem of perpendicular bisector of a chord, as I have shown you, using the relationship which we have learned, and you will find the resulting solution to those problems. Now let's see how parachords looks like and how we can see the relationship between parachords. And you will find out that I have drawn out a circle here, having two straight lines which are parallel to each other here. And these two straight lines are touching the circle at each different point, like point P and Q for the first line, A and B for the second line. And we are finding we have the center O at that point. So in case we extend, in case point O is extended to B, to to B and A, you will find that the extent there, that is OA and OB, are the radius of the circle. So meaning those are the radius of the circle. The same if you extend the point O to P and O to Q, will be still the radius of that circle, that case. This one is still the radius of that circle. But what if we draw a perpendicular from the center of the circle to, we have dropped a perpendicular from the center of the circle to line PQ, to cut line PQ at M. You will find out that it will form a right angle triangle on both cases, and we have seen if you use perpendicular bisector chord, we saw that if you drop any perpendicular or any bisector of the angle which is subtended by the chord to the center of that circle, it will always cut that chord into two equal parts. So meaning that if I produce this line OM to meet line AB at N, I'm also going to have the same thing. Even triangle ONA and ONB are congruent because they are having both a 90 degrees measure, or they are right angle triangle, and meaning that if R, this is R and that is R, the size of that triangle of OAB, then it means the triangle is isosceles because it is having two sides which are equal. And from there we can deduce that triangle, actually the angle here which we have here, this angle OMP is equal to angle ONA. Now here we are finding that that angle will be equal, and this angle here and that one are always in corresponding. The same applies to the other angle, which is OMQ and ONB. They are also corresponding to each other because they are on the two sides of the parallel side, the two parallel chords, and they are differentiated or divided using the line OMN. So from there we can say that the triangle ONB is similar to triangle ONA in such that they are having the rule of right hand side rule, because this side and the other side are the radius of the circle, and one of the angle there we are having 90 degrees and 90 degrees, so meaning they will be similar or congruent with the right hand side rule. From there we can see, as you can see, that if you drop any perpendicular which will bisect the angle and cut the two chords which are parallel together, you will find that it is cutting them into two equal parts, that this one is a half of line PQ and this one is another half of line PQ. The same apply to this. This is a half of line AB from A to N, and N to B is a half of line AB. So that is what we are having there. And from there we can say that if you drop or any chord, any straight line dropped from there, you will find it will cut that any given chord into two equal parts, and that is, it will have 90 degrees. But what if we having some more parallel lines passing through the circle? Let's see what will happen. So having some parallel lines like this which are throughout the circle, and you find that if you draw, you are only having one line which will cut all the parallel lines into two equal parts, in that these all lines that will be on the right hand side will be halves and those on the left are halves. You will find that that chord will be a special chord, and it is what we refer to as the diameter of that circle. So meaning that diameter of a circle is a special chord on which, if we are having parallel lines running through a circle, it will always bisect the the chords into two equal parts. So we are having that, having a parallel chords or some section of parallel chords, then diameter will always cut that chords into two equal parts. So we shall see some of the problems pertaining the parallel chords, and we see how we can handle that problems and how we can give results or solution to given problems with their condition. So let's see some of the examples. One of the examples is that PQ and RS are parallel chords of a circle and 2 cm apart. If PQ is 8 cm and RS is 10 cm, find the radius of the circle. So what we are going to do, I'm going to construct a circle, and after constructing this circle, I will construct it using any radius because I don't have a radius here. Then I will draw the two chords, which is PQ of 8 cm and PQ and RS, and then I construct with them together having 2 cm apart. And then follow the condition here, which I have been told that PQ is 8 cm and RS is 10 cm. And find out what is the radius of that circle. Let's do it together. I'm having a circle of that kind, and in that circle I'm going to give or to draw two chords. One which is 8 cm, so I will take one as 8 cm on the lower part here. And if you measure yours to be 8 cm, and if you want to measure or to construct that one, you do measure any given length. You use your pair of divider, if this is a pair of divider, before constructing. Then you measure 8 cm. Let me see how mine is. Mine is almost 8.5 cm. So, using my given scale of measurement here, I'm having almost 8.5 cm. So, here I'll give you two options. One of the options is either you draw it to scale, or one you draw a circle, and then whatever you have been given, you give it as a sketch. If you draw it to scale, after just drawing you draw first chord and then you draw the second, and you bisect the two, you will find that it will pass through the circle, the center of the circle. Then you make sure that the circle you draw touches the end points of that chord, two chords, and you will find the length of the radius. Another method, or which is much more simpler, you just draw a circle, draw two chords in within that circle, like this one, and name it 8 cm, of which this is the best method to use. And then you draw another one which should be 2 cm apart. Should be 2 cm apart. And if it is 2 cm apart, you will find this one will be at a point here. And this one we have been told is 12 cm, if I'm not wrong. It's 10 cm, and that is what we are calling RS. This is PQ. So having so, the center of the circle will be at that point. After drawing, that is what I used as the center of the circle. So will be at that point. And if that's the case, then it means that if I extend the line to meet from O to meet R, then that will be my radius. The same applies to the other side, that is the radius. And if I do the same to P, I will find the distance from that point here, from that point to P, is still the radius, the same as the distance to Q, is still the radius. So having that, we can say, here we're having that is 2 cm apart. So if this one is 2 cm apart, so I will construct or draw a perpendicular bisector of the two chords, and you will find it will pass in a point like here. Mine is not drawn to scale, so if that one is like sketch, I want to use it to calculate whatever I'm giving out. And I know the distance from this point to here I've been issued with, and this one here is 2 centimeters. So I need to calculate the radius r, is what I'm missing. But remember, if that OM, let's cut this point at M and here at N. So meaning M and N, M to N is 2 centimeters, and OM I don't have. Let me assign that one as X. The distance from the center to chord M, using the same perpendicular which is produced to N with a 2 centimeter extension, we shall find that the distance there is X. So having that, now let's find the radius. Since we are having that, we can either use this triangle OPN, or we use triangle ORM to find the radius. So let's see what we shall find. So if this one is 90 degrees, this one is 90 degrees, then it means that the chords have been cut into 2 equal parts. If this chord was 10 centimeters, then it means here it will be 5 centimeters and here will be 5 centimeters. The other chord will be divided into 2 to give us a length of 4 centimeters each side. So having so, we can use the Pythagoras theorem and calculate the distance of r. So meaning that if we need the r, which will be a hypotenuse to each side of that triangle, we shall take the triangle ORM, and if that is the case, we shall have that if I need r squared, I will get the base of the triangle, which is 5, so 5 squared, then plus x squared. So this is 5 centimeters squared, so I will abbreviate it as 5 squared, and then the units will be substituted later. So that is how I will find in case I use triangle ORM. So let's see, if you use triangle OPN, what will I obtain? This is for triangle ORM. So I'm using triangle OPN. Let's see what we'll obtain. So I will find, to get r squared will be equal to 4 squared plus, now this one, the height has been extended, so the height is 2 plus x, so I'll have 2 plus x, but I'm going to square, it's one unit, one measurement, so I will square both of them, and here we are going to have r squared is equal to 16 plus 2 squared, you will get 4, and this one, if you expand, you're going to get 4 plus 4x plus x squared. If you expand, that is what you will have. So if you collect the like terms, you are going to have r squared is equal to 16 plus 4, you will get 20 plus 4x plus x squared. But remember, we are having two common terms of r. So we're having the first one, which is equal to 5 squared plus x squared, and the second one we have there. So meaning the left hand sides are all equal, so we can equate, and instead of writing r squared or r squared, we shall replace what is here. So on replacing, we are going to have 5 squared plus x squared is equal to 20 plus 4x plus x squared. So after doing that, we are going to have or collect all the like terms, and if we collect the like terms, we are going to find that if we do that, we are going to have, let this one be taken to the right hand side, or we do subtract 5 squared plus x squared from both sides, we shall have 20 plus 4x plus x squared minus x squared minus 25 minus x. There is no additional of x. The first one was x squared, so I subtract, and then minus 25 is equal to 0. If you subtract from both sides, you are going to get there 0. So meaning that 20 subtract 25, you will have negative 5. Positive x subtract x squared minus x squared, you will get 0. And this is 4x. So we are going to have 4x minus 5 equals to 0. Meaning if you want the value of 4x, you are going to get, you will add 5 on both sides and you will get 4x equals to 5. So meaning the value of only x is going to be, for that one you divide both sides by 4 to get x equals to 4 or 1.25, which is similar to 1.25 centimeter. So x here we have found the length of x and we are having x as 1.25 centimeters. So meaning that the distance from the center of the circle to the end is equal to 1.25 plus 2, which is equivalent to 3.25. Or you can use the other triangle, upper triangle, to find the radius, or use the lower triangle to find the radius. Will still give you the same. I will suggest let's use the upper triangle. You will find that r squared, we have said it will be 5 squared now plus x, and x we are having 1.25. Now we square, and you are going to find this one is giving us 25 plus 1.25 squared. Let's see what we shall find. We are going to see that the total of that one is going to give us 26.5625. Total is going to give us 26.5625, whereby 1.25 squared will give you 1.5625. Now, this one is equivalent to r squared. If we need r alone, we are going to find the square root on both sides, and you will find that the square root of 26.5625 will be equivalent to 26.5625 is going to give me 5.1539. 5.1539. This is what I'm getting as the radius of that circle. So the radius r is equivalent to that. And if you use the other way, where the base will be 4 and the height will be 3.125, you should get the same answer as this one. So we are going to have the radius of that one to 2 decimal places. We are going to have the radius as 5.15 centimeters. So that is the radius of that circle. If the chord is 10 centimeters, the two parallel chords is 10 centimeters and 8 are separated with 2 centimeter distance. So we shall have the radius of that circle be 5.15 centimeters. So let's see how we can find equal chords. If we are having equal chords, I'll construct a circle as given below. So if we construct a circle as below, we are going to see that in equal chords, let's have one of the chord to pass through this section here. In that part, so let's have that chord as A, B, and CD. So this one here will be our center O, and if that one is the center, you will find out that if you measure the distance from that center to the other chord there, from that to B here, will be similar to that measured from that point, and this is the radius of that circle. So that distance is the same distance through measuring to the points which attach to the circumference of that circle. The same applies to the other circle, to the other vertex at that point which joins the circumference with that chord. So we are going to have a sample which looks like that, whereby AOB and OCD are triangles, of which these ones here are all radius. So if we may note that way, we are going to have this one are radius, whereby chord A, B, and chord CD, they are equal. They are having the same length. So if that is the case, and as we can see here, we are going to have the two sides which are equal, meaning that if two sides are equal, the base angles must always be equal. And since these sides are equal to the other sides, thereby it always means that this angle here will be equal to the other angles, because we are having the base angles equal at this point, since this is the radius. The side which substance called CD is the radius, and the one which makes the OCD as a triangle which is isosceles, the same to the other one. So we are having that one. Meaning that if this angle is theta, then throughout we shall have angle theta as that. This is the substance at the center or the circumference, and we can see that is what we are going to have. So we can see that if you are having two chords in a circle, they are always equidistant from the center of that circle. Since you having the distance from here to here is the same distance to there, which is the same distance to the other vertex, and that is the radius of that circle. So if we can do a perpendicular bisector to that chord, in that we find what is the distance from there to here, we shall find if this one is cut at N and this one is cut at, let's say, M here, you will find this distance here, which I may call it X, is equal to the other distance, which is also X. So we are finding if you are having two chords in a circle, they will always be equal or equidistant from the center of that circumference if they are equal, and vice versa. Meaning that if the circle we are having equal distance from the chords being equidistant from the center of the circle, then that chords will be equal to each other. Let's see an example pertaining the same. Now, our example here will be that let's consider a circle of radius 5 centimeters and has two equal chords, and these chords are 3 centimeters from the center of that circle, meaning that they are equidistant from the center of the circle by 3 centimeters. So if the radius of the circle is 3 centimeters, we need to find the length of that chord or each chord. So we shall do this. Where the R is, we are going to replace by 5, and this one by 5. And since we have been told there are 3 centimeters from the center of the circle, then here will be 3 centimeters. And the radius is 5 centimeters. So we need to find the length of the chords. And that, if that one is the case, we shall still use the relationship, and we have that this one here will be right angle triangle. And if that is the case, we are going to have one of the triangles, since this chord is the same with this, meaning that whatever will happen on the upper chord is the same to the lower triangle. So if we have that, we are going to cut one of the triangle, and if we do that, we are going to have ONB, whereby this one we are having as 3 centimeters, and this is 90 degrees, and here is 5 centimeters. So if that is the case, we only require to find this point here, which I may call point P. So if that is the case, we can use Pythagoras theorem, and we shall say that if we need P squared or P, we need to find the square root of the hypotenuse minus the height squared. So if it is P squared, then it means we shall take 5 squared minus 3 squared. And that one P squared is going to give us 25 minus 3 squared, we are going to get 9. And if you do that, you are going to get the answer is 16. But we need P. So to find P, you need to find the square root on both sides. And finding the square root on both sides, we are going to find that the square root of 16 is going to be 4 centimeters. So meaning that P is 4 centimeters. So NB there is equal to 4 centimeters. But that isn't the length of the chord AB. And since we say that perpendicular bisector from the center will always cut the chord or a given chord in a circle into 2 equal parts, so it means that if this side is 4 centimeters, the other side will always be 4 centimeters. So meaning the whole chord will be 8 centimeter. And if that is the case, even CD is 8 centimeter, because we were told they are equal chords which are equidistant from the center of that circle. So if we have that, we are going to find that the length of the chord is 8 centimeter. And you can use the same relationship and whatever we have learned, even to find the angle theta, and also to find whatever is included in that as the problem containing equal chords. Let's now see intersecting chords. And under intersecting chords, we are going to start with the first section, which is those which intersect internally. So we shall see at internal intersection. These ones are the chords which intersect inside the circle. They will intersect inside a circle. So in case we are having a circle, for example, I shall draw one. Having a circle of that kind, we shall find that we are going to draw some two intersecting chords inside that circle, such that we have one of the chord in this direction, and the other one be in the other direction. Whereby the center of that circle was at this point. So meaning that the chords which I draw, they are not the diameter of the circle. This is the center here. Oh. So that chords are not the diameter of the circle. And say that if this one is a chord, let me give that one as MM. And the other chord, give it XY. And let's say that they intersect at a point K. So if we do take that, we can denote out that if we have that, then it means here we are going to introduce some things, and we are going to say that if we cut that way, we are going to have another chords like Y, M, and L, X, but they are only to help us extend L, K, X. They are not intersecting, but the ones which are intersecting are L, M, and Y, X. So we are going to use that relationship to find out what we are meaning, and we shall find out that if you find the angle XLM, this angle here, angle XLM will be, or just let's say we just make it up to, actually let's just be M. So if we take that angle, we shall find that angle is equal or similar to angle XYM. Reason being that the angle are similar or equal because if you view this angle here, you will find that it is subtended actually by an arc length XM, this arc length. So you are finding this angle here is subtended by this arc length here. So we are having that angle subtended by arc length XM. So if we say it is equal to angle XYM, you will find out that the same angle XYM is having the same substance of that arc length. So we can see that way. So there is the relationship between the two angles, and the same applies to the other angles here. And you can tell me to what is the arc length being subtended to, and if that is the case, we can say that angle LXY is equal to angle LMY. Then the reason, that one you will give me because I have given the initial, and the same applies to the others. So we can say that way, and we can see, if you view it very well, you will find out that if you find this angle here, which is here, not in the middle but at that point, is equal to the other angle, and this angle here is the same as that angle. So we can say that angle LKY is equal to angle XKM. And that one I'll give you a reason is that the two angles are vertically opposite to each other. If you find this angle is on the upper part, but it is opposite to the other part, but vertically, you can find this one is on top and this one is on the bottom of the other side. So they are vertically opposite angles. So we can say this one are vertically opposite angles. So that is what we can find there. So the same apply to angle XKL, this angle, and that angle YKM. The same applies, and the reason you can give me the reason. So having that, we can say that since we are having that, we have found that this angle here is similar to this angle. The other angle here is similar to that angle there. And this angle here is similar to that one. So we can say this, that triangle XKL, triangle XKL is equal to triangle, the other triangle which is YKM, and this one will have a relation of equiangular triangle or angle side angled rule. So we are having angle, so it is angle and then one of the side here which is similar. This side here and this side is equal. So we can say this one are equal. So the sides are equal. So it is angle, they are similar. So it is angle, side, angle rule. So we can say they are equal by angle, side, angle rule. Or we can say they are equiangular triangle. So since here is equal to this, the other angle here is similar to that angle. This angle is equal to this. So we can say they are equiangular triangle. The same is that we can denote another one that if we need to find the length of that chord, then it means if you take LK, the ratio of LK to KY will be equal to the ratio of XK to KM. Let's see. Therefore, we are saying that if you take LK, the ratio of LK to YK will be equal to KX to KM. So meaning that if we do the other way, we are going to have LK multiplied by, I'll use dot sign to mean that I'm multiplying the two. So if I take LK multiplied by KM, is similar to taking YK multiplied by KX. So meaning that the distance from here to here, if they are to intersecting point, multiplied by the remaining one, is equal to the distance of the other chord to intersecting point multiplied by from intersecting chord point to the other side. So that is what we are having here. So we shall be using this relationship to calculate the missing part or missing length of a given chord which intersect internally. So let's see an example pertaining the same. An example, we shall use that circle and the two intersecting chords, that is X, Y, and LM, intersecting at point K, and say that from K to M we are being given is 6 centimeter, and from K to Y is 8 centimeter, and the other one here we are having as 3 centimeter. So you're being asked, calculate LK. So to find LK there, what you require is to use the information I have already given you, is that if you take LK, you multiply by KM, you will get XK multiplied by KY. So if that is the case, we are going to take LK, which we don't know, we multiply by KM, and KM we are being issued with the 6 centimeter, is equal to 3 centimeter multiplied by 8 centimeter from the diagram there. So this is the first part which is missing. So let's just substitute it by KX so that this one becomes X. And the other one is 6. The other part here we are having 3 and the other one 8. So if we do that, we are going to get 6x centimeter is equal to, this one will give you 24 square centimeter. So if that is the case, to find the value of x, you need to divide both sides by 6 centimeter, divide both sides by 6 centimeter. And you are going to get that x alone will be equivalent to 4 centimeter, because this we shall be divided that way, and we get x is 4 centimeter. So meaning that our x here is 4 centimeter. So that is how we use the relationship in internal intersecting to find any of the length which has been missed from the intersecting point to the circumference. As for that case, we have seen how you can calculate. The same will you apply in case you have been asked an angle, or you have been asked to find the length which is missing. You will use the same relationship and find out. If it is an angle, just make the angle to be in a point of a triangle. If it's this point here, you just cut that time to make it look like a right angle, to be a triangle. Then construct a perpendicular from the center. Actually, from the intersecting point there, you will have it from the intersecting point to that chord, and you will find that if you construct from the center of that intersecting point to that, you will have a right angle triangle, and you will use that one to find out the angle which you require. So let's have a circle with the center O, and if that is the case, that is a circle. I will construct two of the chords. We need to see external intersection. If you construct a line that touches two sides of the circumference of that circle inside and still is produced outside, then that line is referred to as a secant. This one here is a secant. So I'm going to construct two secants. One will be in that direction, and another one I will construct it in the other direction. So that is what I'm going to have. And do call this one as A, where it cuts the points, and this one C, and this one here D. But the point where the two intersect, I'm going to give it a name as C. So if that is the case, let's deduce out some of the theoretical information from this, and we shall find out that from the previous, we have seen if we extend this part here, in that this one here touches here. Let's say we have here, and this other in that direction. We shall find out that they are still intersecting, but those are just lines to help us find out some information from that. And we can say that the lines which we have intersected inside, they will refer to internal intersection, but we are now seeing external intersection. And if that is the case, we are going to see the relationship between A, B, C, D, and O. Sorry, let this one be E. Or give it another, let's just use whatever I used here, which was here C. This is P. And this one be given the name Q, so as to make things easier. So we shall find out that from the previous we had information that this angle here will be similar to the angle there, since because they are sharing the same arc length. We can see that this angle here, the angle PQA, is equal to angle PBA, since because they are having the same or subtended by the same arc length to the circumference of the circle. The same applies to angle here. Let's call this angle theta, and this one also here theta. So we can have this angle, we may give it as alpha, and if that is the case, we shall find that that angle is subtended by the arc length BQ. This arc length here is subtended by that arc length BQ. But you will find out the same arc length subtends angle BPQ that way. So meaning this one is also alpha. From that we can denote that the angle PBC, which is on the AB produced to C, we are going to have that angle as, let me give out B, that is angle PBC, I'm going to find it will be equal to 180 minus theta, because they are on the straight line. And if they are on the straight line, it means angles on a straight line all add up to 180 degrees. And if we are having this angle as theta, then this one will be 180 minus theta. So the same applies to the lower angle, because this one is theta and is still on the straight line, then it will be equivalent to the upper angle, and that one is angle AQC. And we can see that since we are having this angle here as 180 minus theta, and this one is alpha, and this angle here is common within them all, that is a common angle between them all, so which will be 180 minus what we shall be having all to get that one. So we shall find out that this triangle PBC, I'm meaning triangle PBC, so the whole triangle here is equal to the other triangle AQC. You may include even B, so it is AQCB and PBCQ. So that is what we are going to have. So this one is still similar to a triangle. Triangle, I will denote it with the letter, this one, and that symbol, and I'm going to have is similar to triangle AQC. And this one is by, they are having the angle, this angle is similar, this one here is similar to this, and the other angle is similar to that. So we shall say the equiangular triangle. That is the rule which connects them together. And we can still observe that if I do take QC over BC, that is, if I take QC over CB or BC, if I take this length, QC over BC, I will find out that that length is equal to CP over CA, the total length. Such that if I work out, I'm going to get, if I take QC multiplied by CA, that is QC, which is the produced part outside, and QC I'm taking as this part here. If I take that, I multiply by the total length from C to P, I'll use dot to mean multiplication, or you just cross multiply here, you are going to get is equal to BC multiplied by CP. And this relation here, you shall be using it to calculate the missing length and also some of the angles in case it is possible in some problems involving intersecting chords that intersect externally. So let's see an example that will guide us on how to work out whatever we have just learned. Now I'm having a circle with the two chords intersecting, which are my seconds here at C. So I shall say chord AB and PQ intersect externally at Q. If AB is 5 cm as we can see, and BC is 6 cm, and PQ is equal to, and QC is 4 cm. Calculate the length of C, calculate the length of PQ. So I'm going to calculate the length of PQ. This one here is missing. So whatever is present has been indicated. So we are going to use that formula which we have used or found, that is a relationship between the chords which intersect externally to find out the missing here. We shall let our missing to be Y. And if we let, we shall say, if we take this length from here to Q, that is QC, which is 4. Let me write from here, 4 multiply by, or just let multiply by Now, if we take the total, will be y plus 4. That is our total, y plus 4. So if we multiply that way, we shall find CB, which is 6, multiplied by C to A. So it will be 5 plus 6, and we are going to get 5 plus 6, you will get is 11. So if you do that, you're going to get 4 multiplied by y, you're going to get 4y. 4 by 4, you will get positive 16. And if that is the case, this one is going to give you 66. After getting that, you collect the like terms. In that, if you want 4y, you are going to subtract 16 from both sides, and you will have 4y is equal to 66 minus 16, which is going to give you 4y as, if you subtract 16 from 66, you are going to have 50. So meaning the value of y, you are going to divide both sides by 4, and you are going to get your y will be 25 over 2, which is 12.5. So we are getting this side here will be equivalent to 12.5. So that is how we do use the information which we have learned to apply it to condition or problems involving intersecting chords externally. So you can use the same to find out the solution of given problems which you may encounter that involves external intersection. Now let's see how we can construct a tangent to any given circle. And in construction of a tangent to any given circle, what do you require? The first thing, you need to have a pair of compasses and a ruler. For your case, you may be a 15 centimeter ruler or a 30 centimeter rulers. For my working, I will use these two apparatus here. If that is the case, we are going first to construct a circle. You may be given the distance or the radius of that circle, or sometimes if not given and you need to construct a perpendicular or to construct that tangent to that circle, what do you require? Open your pair of compass to any radius, then draw a circle of that given radius. So I'm having the circle as you can see with the radius O. After drawing a circle of any given radius with that one, produce or draw a line from the center of the circle such that it is a radius to touch the circumference at a point, let's say X, such that for my case I'm going to draw that line to be my radius here, and it will be that one to touch there at X. If that is the case, if you want to continue in order to construct a tangent to that circle, produce OX such that that one will be your line now to be helping you on how to construct that tangent. And if we do produce OX, it means we are going to produce a line which is of the same length with our OX in order to find that perfect length. So what I will do, I will still take the radius which I used. That is my radius there. So I'll give an arc like that. Then I extend the line OX to that arc such that we are going to have that way. Now, if this one was my X here, I will call the external point there, let me give it point P. Such that that is point P in that from O to X is equal to XP. Now having that line OP, now construct a perpendicular bisector to line OP. Opening any radius with point O as the reference, draw any two arcs on the upper sides and down parts of the line as that. So with the same radius, draw same arcs to cut the original constructed arcs like that. Then join the two arcs from the point where they do intersect. So having constructed that, you will find that this is the point where that tangent cuts or actually touches the circumference of that circle. We are having at that point. So you will find it touches at the extreme side of that circle. So that is the procedure of constructing a tangent to a given circle. And you can see how it is. As for instance, if you bisect this tangent here, if you bisect or you draw a normal to this tangent, you will find that that normal or a perpendicular bisector of the tangent will still pass through the center of that circle. So meaning, a perpendicular bisector of a tangent will always pass through the center of the circle and vice versa. So we can see that the radius of this circle and the tangent are always at right angles. So they are 90 degrees to each other, meaning that they are perpendicular. And we can notice one more thing, that if you construct a tangent at given point on the circumference of the circle, for example, as we took OX, you will find you will be able only to construct one given tangent. You cannot construct much more than that unless you move from that point to another one as the circle evolves or the circumference goes on. So that is how we do construct a tangent to a given circle, and we can use the information to do some of the practicals or problems involving tangent. In that, let's see one we have here. We have been given an example, or we are going to do an example whereby we will be told to calculate the area of the circle formed when a tangent is drawn and is 15 centimeters, and the distance from the center of the circle to that tangent is 17 centimeters, meaning that in a second. So let's see what it does mean. There is my example whereby this is O, this is P, and the point where the intersectors are. By this side we have been given 17 centimeters and the other one is 15 centimeters. Then we have been told, using that relationship, we should construct, we should actually find the area of that given circle. To find the area of the given circle, we need first to find the radius using the relationship, and from here we can see that the line PR is tangent to the circle since it is making a 90 degrees with the radius of that circle. So if that is the case, we can use Pythagoras theorem to find the radius, and we can say the radius R can be given by taking the square root on both of 17 squared minus 15 squared, of which will give us the 17 squared is 289 minus 225. We are going to have a square root of, if you do subtract, we are going to get square root of 64. And the radius of that square root will be equal, or the square root here will has given us 8 centimeters actually. So, meaning that the radius of this circle is 8 centimeters. And having the radius now, we can calculate the area. Since we know area of a given circle is given by pi r squared, whereby pi is constant and this pi is equal to, we shall use, it is either 22/7 or you use 3.142 in case the number or the radius given is not divided by 7, or if you are not being issued with. So for our case here, we shall use 3.142. So if I have given you the area, I have helped you to find the radius using the relationship. Then I need you to find the area taking pi as 3.142 and radius as 8, and see what you will find as the area of that circle. So that is how we may find problems involving the tangent to a given circle. They may be either on both sides, or you may find a tangent at the other side and another one on top. But that is how, if you want to construct a tangent, that is the process of constructing a tangent. Now, we need to construct two tangents to a given circle, and you will be given or issued with a circle or any given radius. And here, for my instance, I have a circle centered O and a point outside the circle, which is T. And you're being told, construct two tangents to that given circle. What you need here, the first thing you need is to join point T to the center of that circle. In that, if you join, you are going to have, for example, let's say our T is at a point here. That is my T. So you join T to the center of the circle, and this was my T here. So after joining to the center, you will have that. Next step, take your pair of compass, bisect line OT to get C, for example. So if I bisect this line, I'm going to have, we are having that, and the point where they do meet, that is what I call C. So I have C. That was the second step. Third step, with the C as the radius, open any radius, with the C at the center of rotation, open any radius and cut the circle at point P and Q. For example, I'm cutting at that point and also at a point there. So the upper point I'm calling it point P, and the lower part I'm calling it point Q. So having that, next thing what you should do, take a ruler and a pen or a pencil, join P to T and also Q to T, such that you will have you are going to have that point here as P and the lower points as Q here. So after opening that, you cut the arcs on the circle, and after cutting, you join the arcs of the circle to T. You will find two perpendicular, actually there are two perpendicular bisectors or tangents to that circle, and if you draw, you will find out that if you join that point to the center, they will give you a perpendicular bisector to that circle, such as this. If you measure this angle here, this angle is 90 degrees, the same way that. So that is how we do construct two perpendicular bisectors to any given circle, given a point and a circle of radius or radius r as shown below. So that is how we do construct. And this point here, we just use it to help us to construct the upper arcs of that bisector or that tangent. So with that, we have come to the end of constructing a tangent to a given circle with that procedure. So we are going to see the properties of tangent to a circle from an external point. I think we shall just use this one. Let's now see the properties of tangent to a circle from an external point. This is my external point, and we have seen how to draw two tangents. So I'm assuming that if you're having two tangents from an external point T, where this one is an exclusive, we shall be taking that and do name that points as they are P, O, Q, and T. So let's see some of the properties. We shall find out that since we have said these are tangents, you will find that angle TPO will be equal to, TPO is this angle I'm talking about, and angle TQO will be equal, TQO will be equal, but they will be equal because we are having that the tangent is perpendicular to the radius. So if they are perpendicular to the radius, then it means the angle that will result there is 90 degrees. So meaning this one will be 90 degrees. So we have observed that, and also we can observe that if we're having triangle ATPO, we are having line OT being equal to line OT of triangle OQT. So OT of the other triangle, and that one is a common line between them all. It's a common line. So that is what else we can observe. And you can also see that this is, if this one is the center of that circle, then from O to P will be equal from O to Q, since that is the radius. So O to P will be equal to O to Q. And this one is the radius of that circle. Since we're having this line here bisecting the two of them, we can say that this angle here will be equal to this angle because it's only a line which bisects the two and passes through the center of that circle. So if that is the case, we can say now, if we're having that, we are going to have the two triangles PTO, that is triangle PTO will be equal to triangle TQO by right hand side rule, because one of the side is equal, or this tangent here is equal, and it is a right angle triangle, both of them, so they will be equal to right hand side rule. So meaning that if that is the case, then this side from P, T will be equal to Q, T. Since we have seen this one is the radius and is common, this one is a common line, and here we are having a tangent and this one is a tangent, then if this one and this are common and there is a right angle triangle, then it means this side QT and PT will be equal. So that is how it is, and we can prove that if we were told to prove PT equals to MT, we have shown that PT will be equal to MT, PT is equal to QT, so we have shown that way, and also angle TO, we are having actually angle TOQ and angle POT are equal. So we can show that by, since this one is a right angle triangle and we are having the two sides which are equal, then it simply means that this angle here will be equal, since this angle and this one will be equal, and whatever we shall be remaining with will be 90 minus that angle, that is 90 here, we are remaining with another 90, so 90 minus this angle, you are going to get this. The same applies to this. So if this one is equal, this one is equal, then it means the angle here will be equal because it has been bisected into two equal parts. So that is the relationship of finding the sides or any kind of given condition using tangents from an external point. So we shall see an example and see how it applies. We have been told the tangent PA and PC are each 12 centimeters long. So here, now this one is changed to PA, this one is PA, that point here is A, and the other one is PC. Oh, this is A, this is P, and this one is C. So PA is 12 centimeters and PC is 12 centimeters each. So we have been told find OP. So we need to find this distance from O to P, and also angle APC if the radius is 5 centimeters. So find angle APC. We need to find OP. Find OP and angle APC. So let's just do it faster. Since we are having the two tangents being equal and the radius is 5 centimeters, we can use that radius and the other tangent to find out the length of OP, we shall take one of the tangent or the triangle which is being held by one of the tangent. For example, we are going to take of the side AP. If that is the case, we shall have triangle OPA. And if that is the case, we are going to have that the base of that triangle is going to be 5, the height will be 12, and the hypotenuse will be what we are seeking, and we can call it y. So meaning, if we need y from Pythagoras theorem, then we need to find the square root of, I think you understand, because if we take 5 squared plus 12 squared from Pythagoras theorem, it will give us our y squared. But I need y, so I have gone the shortcut. I will take y equals to square root of 12 squared minus 12 squared plus 5 squared, which will give me 144 plus 25, and you need to find the square root of the 2. So this one is resulting to 179. 169, I mean. So this is 169. And you need to find the square root. So y will give you 13 centimeters. So we are going to get our y here is 13. Y is 13 centimeters. So if that is the case, and you need to find the angle APC, this angle here, it is actually the total angle, this one. Let's call theta. To find theta, then it means if we use the same triangle to find one of the angle, we shall say theta over 2, because it will be divided into 2 parts. I'm calling theta over 2 because the total of it will be theta. But if I take only one part, which is this angle here, I'm going to have theta over 2. So it will be equal to, we understand that if you take 5, actually, the sign, let's use, I think you understand what we do mean by SOHCAHTOA, the formula of finding, or in trigonometric 1. Whereby if we want to find the sine of a given angle, we did say, if the angle is theta, if we need the sine, it will be the opposite, which is O, and over hypotenuse. And if it's the cos of that angle, then the cos of the angle will be equal to adjacent of the angle, and you will divide it by the hypotenuse of that angle. The same will apply to tangent. If you are finding the tangent of that given angle, then you need to take opposite over adjacent. And here, what do we mean? If this is the angle theta, 5 here will be the opposite to that angle, and adjacent is the side which lies with that angle. So this one will be the adjacent of that angle, and this one is the hypotenuse. In that case, if we are finding theta, the same applies. So for our instance here, we shall say we are having theta over 2. So we shall say sine, because we need to find the angle and we are having opposite, and let's just find the tangent. So we shall say the tangent of that angle, and my angle is theta over 2. That is the angle I'm finding, is equal to opposite of the angle I'm having as 5. So it should be 5 over the adjacent of the angle which lies within the angle and is not hypotenuse, is 12. So I'm having 12. So if you divide this, if you want to find theta over 2, then you need to find the tan inverse, or the inverse of the tangent of 5 over 2. And we shall get, on doing with the calculator, I'm getting the tan inverse of 5 over 2. So meaning theta over 2 will be equal to tan inverse of that answer. We are going to have it as 22.6198. So 22.6198 with a continuous of some of them, 22.619864 up to other. So 64 again. That is by using calculator. But now we need it in degrees, and let's just take to 2 decimal places. So meaning theta over 2 to 2 decimal places will be equal to 22.62 degrees. If that is the case, I'm going to have theta, which I require, then it will be equal to, I multiply both sides by 2 to get 45, actually 45.14 degrees. That is the value I will get if you multiply that by 2. So meaning the angle here, the angle theta there is equal to 45.14 degrees. That is how we use the relationship between an external point connector or an external point and the tangent to that circle using that external point. You can use it to find any of the given using the Pythagoras theorem, and you find the problems and also the solution to those problems using the same conditions. Let's now see how we can find tangent to two circles. And we shall start with an exterior or direct common tangent. Here you will be issued with the two circles, or you'll be given the measurement of two circles, radius of a given circle and another one, and then you'll be given the distance between the two circles, or the distance between the 2 points of the radius, or the center of that radius. For example, I may have one here. I will draw to any radius. And another one here. So you may have two circles as given as that. And in these two circles, like this one may be with the center Q, and this one with the center, let's give them another names. Let's assign this one O2 and this one center O1. So having those two circles in that one, and you want to construct direct or exterior common tangents to both two circles, what you do here, the first thing here, you join this O1 to O2 using a straight line. We are having that. After joining the two, with the center O1, we are going to construct a circle which will be the radius of this larger one minus this one here. For example, if this one is of radius, let's say this one is of radius R2 and this one be of radius R1, then the circle which we need to construct should be R1 minus R2. That's the circle which I want to construct. So let's construct that circle here at center, with the center O1. So I shall take the radius of this and subtract that of here and find what we can find here. We find it's approximately to this. So having that one and this one as the center, construct that circle here. Well, the circle which I constructed. Now this circle here is of radius R1. So from here to here is R1 minus R2. That's the radius of that circle. So after doing that, the next thing you should do, let's go on and construct a perpendicular bisector to line to line O1 or 2. I'm going to bisect that line to get line N, like a point N on the line O1 or 2. That way. Where intersection takes place, I'm going to name that line as N. Now after doing that, I'll take that N as my center. So having that as my center now, I'll take my pair of compass and place it at N, but having the radius O1 N, I'll take it this way, place it at this point. So taking the radius ON, I'll take up to O1N, that's my radius. With the same radius, which is O1N, I will cut the circle whose radius is R1, R2. Two arcs, one at the top and another one at the bottom part. That way and this way. Then after doing that, I'm going to join. I will first name, let me name that one as, let me give it as R and S, so that this one is R and this one is S. Then I'm going to join R to O2 and S to O2. So on doing that, we shall have, we are going to have that 2. Now after constructing that R, joining R to O2 and S to O2, using that way, you will find that the point where they touch the curve and that cuts as arc is meaning that they are tangent at that point. So what we shall do, we are going to join R to O1 and also O1 to S or S to O1. So on joining you are having that, and if you may view it keenly, this point here is 90 degrees, this angle also is 90 degrees. So meaning that angle OSO2, O1SO2 is equal to 90 degrees. Or the lines which we have drawn internally, that one, have formed 90 degrees with the circle of R1 minus R2 as the radius. Now, what you do next, produce O1R to meet this larger circle of radius R1 at, let's say, point X. So I'm going to produce this one here to meet that circle at X. I'll call that point X. And also to produce O1S to meet the circle of radius R at point Y. I'll call this point Y here, where they meet with the circle. So if I have in that, then with the same, I'm going to construct a parallel. Actually it's a parallel line to this. So if that is the case, I'm going to construct another one to be Q and T and M. That is T and M. I'm going to construct a point T and also M, but which is parallel to this O1X. And to construct that, I will use this line. I want this to be parallel with what I'm going to construct. Now to construct a parallel line which is parallel to line ORX, you need a ruler and a pair, actually with one of the set square, you can use this or the other one of 45 degrees each. So you place your ruler not on this line, but on the other which makes perpendicular with the circle R minus R2 as the radius. So on placing that, you place your ruler that way, then you start with there, where the lines are actually making 90 degrees, and then with that, this set square, slide over that ruler until you find where your center here is and that one is. So you will find it is cutting at that point here. So that is the point where you will mark that point as we said T. So meaning this point will be our T. And if you may view very well, you will find that one is parallel to this line here. So that is what we shall have. And on the other case, if you want to draw the other on the downward part, you also put your ruler on the line which is now O joining S that way. Then using your sliding square, let's use this one here. Then you place it in this direction. Actually, which one it calls? This one is the best. So you place this one. the ruler that way, and then this one in that direction. You will find if you are drawn to scale, it will come, and then you slide your ruler over until you come up to that point where it is that way. So you will find it cuts at that point here. There is where the line is cut. So you will take your pen of that way, then you cut the given point, that point there, then you join the point to the center where the center is there. You join that way. You will find that side is that line O2M is parallel to line O1SY. They are parallel. After doing that, remember, I've told you in order to construct a parallel line or radius in that of circle R2, you need to take your ruler and a set square, slide it over this point here. Because this is 90 degrees, then a set square will help you to construct a parallel at the other side. The same applies to this side here, and it will also help you to find that side there. So meaning, at this point where you will find this one will be, actually it's not that way, but it will be greater than that. So we are going to have it's still 90, because we are using set square, it will give us 90. This one is also 90 degrees. So we are going to have it in that section. So what we are going to do, you will take your pen and your pencil on the ruler, and at the point where the two curve the circle, you draw a line joining the 2 points as that. The same applies to the downward part. You draw a line joining the 2 points. So on drawing that way, you will find out that it will form that way. And then at this angle, if you measure this angle, you are going to get that angle is 90 degrees. This one here is 90 degrees. The same applies to this one is 90 degrees. And here is 90 degrees. So meaning that whatever we have drawn is a tangent to circle, this circle here, and also this. This line XT and line XOM, actually line YM is what we refer to as direct common tangent or exterior common tangents. That is how we do draw. Just a recap, draw the circles which you have been given. Draw a circle which will be in the larger circle but is that of the larger circle's radius minus the other circle's radius. Construct that circle and then construct the line joining the two center of the circles together to obtain a center at that circle. Then using that one as the center and the radius of the larger circle, construct 2 arcs at the center where R1 minus R2 is as the radius, as we have done. After that, join point O2 or join O2 to that R1 or the way the arcs cuts the smaller circle in the larger one, as we have done here. For us, we join with the R and S. After that, produce this line here, which was from O1 to this. Produce it to go up to the larger circle where R equals to 1, R1. Then the same to the other side. After producing, construct a parallel line which will be parallel to the radius of the larger circle in the other circle, as we have done. And I've said to do that, you need a set square to help. After doing that, then the point where they join or cut the circumference, join those 2 points, and you will find the points will give you a parallelogram, or actually they are giving you a tangent. And from there we can denote some rules. We can see that this X O2 T and SO2YM. We are finding is a parallelogram because it resembles a parallelogram, and since we have said this is a tangent, it's a parallelogram with each angle equals to 90 degrees. And we know a parallelogram with each angle equal to 90 degrees is a special parallelogram, and that is a rectangle. So meaning that this one here is a rectangle, and also this one here is a rectangle. If you view, you're going to get a rectangle in both cases this way. Those are two rectangles. And since we have obtained that one, we can still use the same information from what we had. And this one will be tangent to this circle. And if you view out the equations and relation we used in the other circles, we will find they are still the same, whereby the line which is from the center here bisects the external one here, which is external to this point, into two equal parts or two equal degrees. The angle is bisected into two, and the angle at the center of this circle is also bisected by into two by this line, and we can find the radius is the same. So from there we have seen how we can construct direct or exterior common tangents. Let's go on and see how we can do the other way of constructing that one, and we shall be viewing a transverse or interior common tangent. Now let's see how we can find transverse or interior common tangents, and here we shall start with the circle. They may be of the same size or different size. I'll take two different sizes, for example, one having R and another one R2, one with the R1, another one with the R2, whereby let's construct and see. I'll take this, my circle here, to have center O, center P I mean, and this one to be of center Q. My circles here are of the same size. So what you do after drawing circles of given radius, the next thing you do, you join the two radius together in order to construct an exterior common tangent. So I'll join the two radius, in this case this way, in that part. So I'll join P to Q. After joining P to Q, now construct a circle where you will find, if this one here is R1, is of radius R1, and the other one is of radius R2, then you need to construct a circle which will be of radius R1 plus R2. So we shall add the two radius in that. Let's view how much is it. So I will construct of the radius which is double. We are having a circle of that kind, whereby the new circle formed is of radius R1 plus R2. For my case, the two radius were equal, so R1 and R2 is equal for this case, but in some circumstances you will find R1 is not equal to R2. In order to construct the outside circle, you need R1 plus R2. So the distance from here to the other side will be R1 plus R2. Now, after constructing that, take your compass, bisect line PQ to find point C, which we shall use as the center for our arc drawing. Now, after constructing the point C, now use that point C as your center, and if you have that point C, you will use it with P in such a way that we are going to have PC as the radius of that circle of what we want to use. So with the radius PC, of which we shall take it as this this kind. So with that radius, cut the circle of R1 plus R2 to both cases, that way. After cutting that way, then join Q. Let's name that circle's 2D dimension. The one which is cut at the top, we give it a name R. Let this one be R, and the arc at here be S. Such that we now join Q to S and Q to R. And if we do that, we are going to have this way. This way, I mean. We are going to have those 2 points. And with the 2 points as that indicated, as R and S, draw a line which touches that arc where the 2 lines are joining and to the center here, so as to find that one as the radius which we are referring to as R1 plus R2. We are going to have that kind, and from this you will say that PR is what we are referring to R1 plus R2, whereby now this one here will be R1 and here we are having R2. So after drawing that, you can see from what we have drawn that this point here, we are going to have a right angle triangle because the 2 tangents drawn are actually tangent to our given circle R1 plus R2. So now, what we shall draw now, we are going to draw a parallel line or 2 parallel lines which are parallel to PS and PR on circle R2. If that is the case, I told you using a ruler and one of the set square, put your ruler on the line because we want to draw which will be on this. So we are going to draw a line which is parallel to PR on circle Q, circle of center Q. So what we shall do, you put your ruler on this line here. After putting your ruler on that line, such that it be in coincidence with the line, then slide your set square in such a way that it slides there on that line. Yeah, actually. So there, where you find your center Q there, you mark that point here as we have here. So we are going to mark that point at that point where the center and what we had drawn has appeared to be. So we shall mark that point here. So this part here, this was our Q, center Q, and here we have found this one is parallel to this side here. And we can call it T. Let's give it a name. Let's suggest one as X. We may give it name X. And here the point where the circle, this circle R1 is cut, let's give this point as M, and this other one here we give it N. And here we construct a parallel to PMR as QX. Now we are going to construct another parallel line which is parallel to line PNS, and to construct that we are going here to take a ruler and we shall place it on this side here on the line, actually it's line SQ. So place it on line SQ drawn. Using your set square, put your set square with coincident with that line PNS, then slide your set square up to a point center there, and you will find your line is cutting the circle at that point. So after getting that point, join the point with the center such that you have to make this one to be y. So we have joined to find the other point y, which is on that part, and this line here we find that is parallel to line PNS. Now after constructing that way, we only remain with one procedure whereby we need to join y to n, and joining y to n, we shall join them this way. You join y to m using a ruler and a pencil or a pen. You will have that, and also join x to m. Now we have joined x to m, and we shall find out that whatever we have drawn here, we are having mx, and also we are having ny. These two here are the required transverse or interior common tangent. So you can see from what we have constructed here, we are having two common tangents of the circle of radius r1, which is inside, and of radius r2, which is outside, with the center q. So if you are being asked to construct a circle of or a common interior tangents or transverse common tangent, what you are just required is two circles, and you construct a circle whose radius is the double of the two, or the other plus the other. For our case, that is r1 plus r2, as we have done here. And after doing that, you construct, you join the two points or the two centers of those circles. After joining the two centers, bisect the line which is joining the two centers, as we did. After bisecting, give us a name where the point intersects with the line, and then using that one as the center, use the center of the other circle with that intersecting point as the radius, cut an arc on the side which is r1 plus r2, both sides, then you give it a name. From there, join that one to the center of the other circle. After joining the center of the other circle, now make a parallel line which is now parallel to RMP on the other side of that circle by using by help of a ruler and a set square. The same should be applied to the other one, and after doing that, you will come to discover that you will have formed a parallelogram here of sides 90 degrees each. This is our parallelogram of sides 90 degrees each, and from this we can say the parallelogram formed is a special parallelogram of 90 degrees each, and that is a rectangle. Actually, we have two rectangles. One is NSQY and another one is MXQR. That is a rectangle. But from what we have drawn, you will find out that QRP is 90 degrees because RQ is tangent to the circle of radius R1 plus R2. From where we can denote that PMR or PR, which is equal to R1 plus R2, is tangent with the given tangent, meaning they are perpendicular. So PR is perpendicular to the tangent. The same applies to PS, is perpendicular at this point S with the tangent SQ. So that is what we can denote. The same can be noted with the circle R1, whereby XM is tangent to the circle of radius R1 at M, so meaning PM as the radius is tangent or is perpendicular to the tangent MX. The same applies to PM and NY. So meaning that what we have drawn here is transverse or interior common tangent. And if you have been asked, that is the procedure for drawing a tangent or transverse or interior common tangent. So we shall see one of the example here, and that says draw two equal circles of radius 2 cm with their centers 7 cm apart, and construct a transverse common tangent to the circles. This one I will leave it to you to work out, and what I will do is that I will guide you through what to do. One thing you should do, take your compass any radius here is being given. We have been told is 2 centimeters. So measure 2 centimeters using your pair of compass. Draw two circles. The first circle here using center of any letter or of your choice. Draw a circle. After drawing, from your center, measure 7 centimeters from your center to the other circle. Then where the 7 centimeter will end, draw another circle of 2 centimeters. That one now will be determined that the two circles have 7 centimeters apart with their centers. So meaning their centers are 7 centimeters apart, but they are of 2 radius each. And then after that, draw a circle which is R1 plus R2, of which will be now 2 centimeters of the first circle plus 2 centimeters of this next circle. So it will be it will be that your circle which you will draw will have a radius of 4 centimeters. After drawing that, then construct a perpendicular bisector to the line which you will have joined the two centers together. Using the point where they intersect as your center, use that one as the radius from the first center, and then cut an arc or make an arc to the circle which will be 4 centimeters of radius 4 centimeters, both sides. Join the point where the arc is made to the radius, to the center of the first circle the same, and then you join the center of that circle to those arcs. After doing so, make a parallel line with that center of the next circle which is parallel to that line which you join with the center. The same should apply on the other side. After making that, now join that one to those parallel points where they cut the next circle, and what will have been formed or constructed will look like what we have on the board, and that is what we do call as transverse or interior common tangent. Let's now see how we can find contacts of circle. And under contacts of circle, we know that two circles are said to touch each other or have a contact when they share a common tangent. So if they touch each other at a point of where they have a common tangent, then we shall say those circles have a contact. So we shall see how that applies in our case. After drawing, as you can see, we are having two cases, one of which we are having is contact within two parts, whereby one is inside the other, one circle is inside the other, and another one is they are on different parts of the tangent. So as we can view here, we are seeing two circles, one which is bigger, another one which is smaller, but they are having a common touch at this point where we have a straight line. This point here is what I'm referring to, a tangent. This is the tangent to both of the circles at this point, and we can say these two circles are in contact because they are all touching inside at this point of tangent. So you will find that this from A to tangent, let's say this one to be tangent 1. So you will find that from the center of this point here to here is the radius of the smaller circle here, So it is having A minus, it is actually A to T1, that's the radius of the smaller circle, and the radius of the larger circle, the center of that larger circle is at B, so meaning the radius is B T1. So we can say that if you want to find the distance from this point to here, amplify to this smaller distance here, let's refer to as S. So the difference in the radius will be equal to, you take the radius of the bigger circle minus the radius of the smaller circle. By doing that, you will have found the difference between the two of them, and we have a common tangent at both of them. So what we are going to do again, we are looking at another one here, whereby this smaller circle is having a center A and the other larger circle is having center B. So as we can view, you will find out that they are having a common tangent, and that common tangent there is going to give us a point of contact between the two circles. And if you want the difference between them, meaning that the distance from here to here, we shall have it as, I'm talking about this distance here, let's call it Y. So that distance Y will be equal to, if this one is our tangent 2, for example, we shall have it as BT2 as the radius of the larger circle plus B actually is AT2. AT2 is the radius of the smaller circle. So if we are having that, you will end up with the difference in the two circles as the distance between the centers of the two circles as BT2 plus AT2. Whereas this one we have seen how you can calculate. So having this information, you can do construct even if you have been given. If you have been given the measure of this one, you will first construct a circle of radius BT2. After constructing that circle, construct or produce BT, whereby you don't know what is BT, so produce that BT outside with the same length, then construct a perpendicular bisector to that line, you will find this tangent T2. After constructing that, using that same line, measure given length of now AT2, now this radius, measure from that tangent to there at the center, and then you construct another circle. The same applies to this. Construct the circle given first, construct a tangent. After constructing the tangent, measure the length from that tangent to the given point which you want as the center. If it is B, measure that length after constructing the circle of the smallest one, and then using that B, construct the largest circle using B, T2 as your length, if you have been provided with. And then you can see the relationship as how we have done. So we shall see an example and work out, which will give us more information on how to work out what we have. Let's see. Now we are going to see an example where we are being provided with circles P, which is a smaller circle of radius R1, and another one circle Q of a larger circle with the radius R2 as we can see and center B, and circle R with a radius of R3 here and center A. So we can also witness another property that if 2 or 3 circles are in contact, then their radius lies on a straight line. And if this point here may be a point of contact, like here, they are sharing the same tangent, so meaning we are having 2 tangents, one here, another one here. So that is what we are having. And we are being asked, find AD, BC, and AC in terms of R, R2, and R3. So we need to find AD. First, we have been asked to find AD. So to find AD, what they require is the distance from this part here to the other part. First, we need to identify, as we said, remember what we said, we did say that if you need to find the distance between 2 points of contact, if they are in contact, outside contact, then you will take the sum of the 2 radius. If they are contact internally or inside, you find the difference between the two radius. That is, you subtract the radius. And here we are having this circle here R, R3, R of radius R3 and R of radius R1 having contact here. So we need the distance from A here to D, meaning it is the distance from A to D, and that one is of diameter here, which we are having diameter of the circle P, because the radius of the circle P is R1, so meaning the diameter will be 2R1. And then the radius of the larger circle R from this point to here is R3. So meaning the distance from here to here is R3. So AD will be equivalent to the distance from A to that point of contact here. Let's call that point as, let's just give it as T1. So that is like tangent 1. So the distance from A to tangent 1 we are finding is R3. So we shall take R3 plus the distance now from T1 to D, of which is T2. So to D. Actually we are having R1 and also R1, meaning if we add together we are going to get 2R1. And that is the distance from A to D. That is how we do calculate that distance. So we are going to calculate another one, which is BC, the distance from B to C here. BC. So we need to observe it clearly, and you will find the distance from B to C. Actually, this is a circle, a larger circle. Let me just extract for you to view it very well. So I'll extract it but not to scale, to make it much more smaller that you will understand it better. So I'm going to extract the larger circle Q in this manner, such that we have that one as circle Q, and then the smaller circle, that is my smaller circle there, as circle P. So having that, we know the center of circle P here is given as C, and this is R1, this one is R2, and here at the center here we are being B, or this is still R1, and here from here to the end here we are being given that it will be, from here to the end we are having as R2. So the distance from here to the end is R2, meaning that BD equals to R2. But we need BC. So to find BC, remember from the point of contact here to the end, we are having it as 2R1. But from C to the D, but CD is equal to R1. If you want now to find BC, you need to take BD, then you subtract CD. So meaning that if you want BC here, you need to take the whole distance, which is BC, then you subtract CD. So if that is the case, BD is R2, as we can see. So it will be R2 minus, then the distance from C to D is R1. So if you subtract R1, you are going to get BC is equal to R2 minus R1. Then we have been asked to find AC. AC. To find AC is like having two circles of contact but externally. So I shall also draw it aside for you to find out. AC, it will be equal to, we are having one circle here and another smaller one here, such that they intersect at that point. So the distance from here to here we're having is at R3. So that one I'm meaning from the center A to the point of contact here is R3. So this is A and this is the point of contact, let's say T1. So that is it. So to see the distance from there to the center here, we shall have it as R1. This is point C. So that is C which I'm talking about. So the distance from A to C now will be the distance from there to the tangent, which is R3. We are having as the radius 3. And the distance from the point of contact here to C will be now plus R1. So we shall have R3 plus R1. Remember these two circles, this circle R and circle P are intersecting externally, and circle Q and P are intersecting internally. So that is what we have noticed, and that is how we can work out the distances. We are going to see angles in alternate segment, and to understand this you need a circle and some chords in that circle and a tangent. So in order to find this, I'm going to construct one circle here which will help us to understand what are angles in alternate segment. Now, I have drawn a circle which will help us to understand it well. And here I'm having a tangent RPT, which will be a tangent to the circle which we are having PAQB. That is our circle with the center out there. You can see the center is within the shaded part. And then we have one of the parts shaded and another one is unshaded. So as we can see, PQ is dividing the circle into two alternate segments. Actually into two segments. One is on the upper side, another one on the lower side. So we can view out that if you find the angle here, the angle there is alternating to the other segment which we have of PQA. So PQA, which is shaded, let's shade the shaded part or angle of APQ in the shaded part is in the alternate segment. Is in the alternate segment with the angle of unshaded part, which is QPB. So QPT. So that one is there. This one should be not A but should be RPQ. Is an angle in the alternate segment with angle QPT. So meaning that the other which is in the shaded region there is in the alternate segment with that of unshaded region down here. And the two goes vice versa. So we shall see some of them. Let's see some examples. If we do talk about this alternating or angles in alternate segments, then this is what we do mean. For example, here we shall see PQR is a tangent to this circle QST, and you will find out that the angle PQT here, which is the angle on the outside side, is on the segment TQ, as we can see this way. So it is in this segment. But you will find this segment here is an alternate with the other one, which is on the other side. So here we shall give out which angles are equal or similar. For that case, we are going to use the help of arc length or the help of a chord. So we shall find out that angle B1 here, which we have at this point, you will find since it is in this segment, it is subtended by this arc length, which is from T to Q. At the same time, is subtended by the same chord, which is TQ. So angle B1 is subtended by chord, we are having TQ, and it will be equal to the other angle there, B2, which we have here, and you can find out that the two angles B1 and B2 are subtended by the same chord TQ. So we shall say B1 is equal to B2, and we can say they are subtended by the same chord TQ. Otherwise, if you don't want to talk about the chord, you can also say that they are also similar because they are subtended by the same arc length, which is TQ. Actually, this arc is starting from that point up to there, and the same for that one is from that point to T. So meaning it's the same arc length or the same chord TQ, and we have found out that way. The same applies to the angle which we are having here as S, angle SQR, we are having this as A1. So we shall find angle A1 is equal to the angle which we have in STQ, and we can say that angle A2 is also equal to that because they are all being subtended by the same chord which is QS, subtended by chord QS. So subtended by chord QS, as we can see, this chord is subtending angle A1, which we are having this way, at the same time is subtending another angle there, which we are having as A2. But we can still talk in the same manner as we said. It's being subtended by the same arc length, which is arc length SQ. The same apply to this angle SQR, the same arc length. So that is how we do give it. It may be in several ways. You may be some of the angles being scattered in that, and we can still say we give the relationship either depending on the chords which subtend them or make them to be on alternate segments, or we give it according to the arc length which they have. Let's see another one. Circle TQUS and PQR as a tangent to that circle, and some of the chords cutting in throughout the circle internally, as we can see that way. So given this one as angle R, this one as T, this one Q, and this one P, you may be asked to show that obtuse angle R is equal to that angle P. Show that the obtuse angle R is equal to angle P. So if you are being given that case, what you should do here, we are going to see how we can find much more relationship with the angles in alternate segment or angles in a circle. So from this one, you should note that if you are having angles in this case, then if you take an angle which is in a quadrature, as we can see here is in a quadratic quadrature, so you can find out that these angles here are being in a special given four-sided figure, as you can see here. So meaning that if you take the angle here, I'm taking the figure to be TSUQ, not cut. So it is all those which touches the circumference. So if you take Q plus P, meaning I'm taking Q plus P, the angles, if you add the two, you will get 180 degrees. And this one are angles in cyclic quadratum. Cyclic quadratum. The same applies to the angle here. If you take this angle and this angle here, should add up to 180 degrees. Reason being they are in cyclic quadratum. So that is how we do determine them. But remember we did say that angle SQR, if we are having that relation in the previous note, you can have that angle SQR, which is T, angle T, will be equal to angle Q. Reason being, they are being subtended by the same arc length, which is SUQ, or being subtended by the same chord SQ. So meaning that angle Q is equal to angle T. Angle Q is equal to angle T. And this one, the reason will give us that angle Q is equal to T because they are being subtended by same chord, and that chord is SQ. Or you can say same arc length and that arc length is SUQ. So from there we can also note that on this tangent we are having R and T as the angles at that point. So if we take R plus T, we shall get 180 degrees, and we know these are angles on a straight line or adjacent angles on a straight line. So we can say adjacent angles on a straight line add up to 180 degrees. that is how we do find them. So if this angle T is equal to angle Q, and we have said that they are being subtended by the same chord, which is SQ, or in different alternate segment. So that means that angle R will be equal to P. Therefore, or thus, angle R will be equal to angle P. And this one here, we are saying that they are being subtended by the same chord, which is SQ, or the same arc length, which is STQ. As you can see, this angle P here is being subtended by arc length or QTS. The same applies to angle R, which is in this position, is being subtended by the same arc length, which is QT and then S. You will find that angle. So they are being subtended by the same subtension of chord, subtended by the same chord QS, or the same arc length QTS. And that is how we do find angles in alternate segment, and some more can be given out. If they are on the circumference, remember to use the formula of cyclic quadrilateral. And if on a straight line, then you know that the adjacent angles on a straight line will add up to 180 degrees. Another formula to note is that in case we have this angle P, let's take another one, actually like that. So we can find out that in case I have this angle, and let me call this one, let me give this angle here, this angle. If that one is my angle, and here is the center of that circle, and this angle, let's give it a name as, let's call it W. So this one, if it's W, you will find that if it is subtended by the same chord TQ, or subtended by the chord TQ, that angle W, you will find at the center, it will be double the angle. So meaning here will be double the angle, so here will be 2W. So meaning that if an angle is subtended at the circumference, then at the center it will be double the angle which is subtended, the same chord at the circumference, or the same arc length TQ at the circumference, as we can see. So meaning if you have an angle subtended at the same at the center and at the circumference with the same chord or the same arc length, then the angle at the center of that circle is twice that of that at the circumference, as we can see. So if this one is W, this one will be 2W. The same applies, and that rule applies throughout. And if you may encounter some of the question, you may use that one to work out. So we shall work out one of more example. We are having a circle TP, whereby this is my P here. So it is TPQS, with a tangent to the circle SR as the tangent, and as another secant, which is PQR. Then we have been given an isosceles triangle within the circle, and the circle is of center O, as we can see here, and isosceles triangle having 180 degrees as one of the angle, and an angle on the tangent, we are having it as 56 degrees, as you can see there. So we have been asked to find X and Y. So we needed to use the idea which we have found from previous knowledge and work out this example here. So we shall start with, if you have angles in isosceles triangle, they all add up to 180 degrees, but two of the base angles must be equal. So meaning that if this is an isosceles triangle, this angle here must be equal to this, because the base angles of an isosceles triangle are equal. But a triangle adds up to 180 degrees. So if you take 108, you subtract from 180, you will have 72. 72, if you divide by 2, you will get each side of the base angle will measure 36 degrees, as we can see. So that is the first measure, and we have found out that way. So we are going again to make this one as a complete. I will make it a complete quadrilateral in that circle. So if that one is a complete quadrilateral, then from the formula I had already given you or knowledge, you shall find that if you take this 108, you add to the base angle here, which are in opposite or cyclic quadrilateral, you should get 100. You should get actually 180 degrees. So using the method or formula of cyclic quadrilateral, so it means that if you take 180 minus 108, you shall get this angle here. So this angle will be 72 degrees. Remember, the angles on adjacent angles on a straight line will always add up to 180 degrees. And here we are having 56 degrees, 72 degrees remaining with this angle here. So meaning to get that angle there, we need to get 180 degrees minus 72 minus 56. So we shall have 108 minus 56, and this one will give us, I'm taking 108 minus 56 because if you take 180 minus 72, you will get 108. And then we are getting 108 minus 56, and this one is going to give us 52. So meaning that this angle here will be equal to 52 degrees. And remember one thing that we said, if this angle here, or let's start with this angle 56. So if that is the angle 56 at this point, we say that if two angles are subtended in a circle with the same chord, then they are equal. So meaning that TS, this angle TS, let's say with this Q, not Q, give it Z. So TSZ is equal to angle TQS. So meaning this angle here will be 56 degrees. And remember the rule. The same applies to angle QSR, which is 52 degrees, being subtended by a chord SQ or arc length QS will be equal to angle X here. So meaning this one will be 52 degrees. Will be 52 degrees. So X equals to 52 degrees and is the same as angle Q, which is equal to angle QSR. And this one we can say the reason is that being subtended by chord, actually is chord, subtended by chord, we are having chord QS, or in alternate segment. So we have found that is what we have. And then we have found this is 52, this is 52, so we have filled out, but we still to find y. Remember what we said, angles, adjacent angles on a straight line add up to 180 degrees. So here we are having 36, 56, we are remaining with a certain angle there. So if we need to find that angle, then we are going to take 180, we subtract 56, and also we subtract 36. Let's see what we do get. You're going to get 128 there. So meaning this side here is 128 degrees. And if you take, now to find y, you are required to take 180 degrees as the total angles in a triangle. They will always add up to 180 degrees. So if you take 180 degrees, you subtract 128 and also subtract 52, we shall find y. And if that one is the case, so we are going to take, now, we have said that angles on a straight line add up to 180 degrees, especially when they are adjacent. If, for example, this one here will give us 180 degrees. So if that is the case, you will take 180 degrees of the total angle at this point, then you subtract 56 and you subtract 36, and if you do that, you're going to get this angle as 88 degrees. But remember, SQR is a triangle with the two sides, two angles being given. So to find y, you need to take 180 degrees, because all angles in a triangle add up to 180 degrees. Then you subtract 88 and 52. If you do that, you are going to get your answer as 40 degrees. So meaning y is equal to 40 degrees. And this one we can say angles in a triangle add up to 180 degrees. That is how we do find that angle. But the other one we say it is subtended by the same chord as the other one, which is QS, and the angle which is subtended by that chord in other alternate segment we saw it as 52. So that is how you can calculate some given angles in a circle or given triangle, and using the rules which we have been learning and we have already learned past, you can calculate any given angle, be it at the circumference, at the center, or anywhere. So that is how we do work it out. Using the information, please try out some of the figures and some of the given problems using the same technique which we have been using to handle out given examples. With that, we can say that if for any tangent to a circle, a chord is drawn from the point of contact, the angle which the chord makes with the tangent is equal to the angle subtended by the same chord in the alternate segment of that circle. And that is what we have seen while calculating and working out the given examples. So with that, we have come to an end of angle in alternate segment. In our next section, we are going to learn how to construct circles and circles if we have been given triangles. Now we are going to see circles and triangles, and from here you may be issued with the measurements of a given triangles, and from there you may be told to construct respective circles from those triangles, in that you may be asked to construct either inscribed or subscribed, or that which is exterior or inscribed from the given triangles. So we are going to see how to construct these triangles and the respective circles. We shall start with the inscribed circles, and if that is the case, we shall start with a triangle of any measurement for our case, because I don't have any kind of measurement here. I'll call my triangle here A, B, C. To construct an inscribed, then you need to bisect each given angle or any of the two angles. In case bisecting of any of the two given angles, what you do here, you are going to bisect or open any radius standing at one of the angle, maybe A, at angle A, cut line AC and cut line AB such that you have two arcs on the two lines. Then after cutting the two lines, using that axe, open any radius or using the same radius, make arc at the center of that triangle that way. After doing that, join the point where the two arcs intersect with the angle, and you will find that the angle is bisected into two equal parts. So that is what we have there, and after getting that, go on by bisecting the other angles. For example, we may select one which is at B, and if that is the case, if that is at B, open any radius standing or having the center as B, cut line BC and also line BA such that you have two arcs on the two lines. Standing at the arcs on line BA and BC, make a bisect at the center of that arc using any radius as we can see here. So after doing that, join the intersecting where the two arcs intersect with B as we have done here. Such as that. So meaning that the point where the two bisects intersect is where we shall use as our radius of the circle which we shall construct. And in that case, we are going to construct a triangle which will touch the sides of that. We are going to construct a circle which will touch the sides of that triangle. I used a small scale, so I believe that you understand with the scale measurement, you understand how small it is. So we are having this one as circle O, center O, and the circle which I have drawn touching the sides AC, CB, and BA is what I'm referring to as inscribed circle. And if this one is inscribed circle, then the center here, the center we are having is called in center, or it's referred to as in center. It is inside a triangle. That's what we refer to as inscribed circle, inside the triangle. And the center we have said is referred to as in center. So let's go on and see how we can construct circumscribed circles. For circumscribed circles, you will be issued with the measurements of a given triangles, or already a triangle be drawn for you, and then from there you will be asked to circumscribe a given circle. I will guide you through which you will use as guidelines, in which you will help you to circumscribe any given circle, any given triangle. If you may be having a triangle as what I'm having here, let's be A, B, C, you may be asked to circumscribe that triangle. And in circumscribing a triangle, you need to construct perpendicular bisector to any of the two sides. May it be B, C, or any of the, or even all the three sides will still intersect at the same point. And then the point where they do intersect, use that point as the radius of that circle which you want to construct, and then construct a circle which passes through the vertices C, B, and A as below. So I may choose point at sides AC and construct a perpendicular bisector to it, such that we shall have an arc of any given length in that way. So I'm going to construct a line which will cut that line and passes through the intersecting arcs that way. After having that line, then I'll construct another side. Let's take that side be AB, so that I open any radius, cut that side, also the other. So after constructing that two arcs which intersected at that two sides, I will construct a line which passes through the two intersecting points of the arc, so that we have that line cutting line AB into two equal parts, because it's a perpendicular bisector to line AB. So after constructing that way, the point where the perpendicular bisector of AC cuts that of BA, and then that point there will be our radius of the given circle. So with that point at the center of our circle, we shall open a given radius, then touch one of the vertices and construct a circle which passes through all the vertices. Let's see how it works. So we have constructed a circle, and that circle has passed through the vertices C, B, and A. That is how we do construct a circumscribed circle. And the point where we have O is referred to as circumcenter. So that is circumcenter. And the other one we refer to as in center. So the point where we have O, the center of this circle, is called circumcenter, and the total circle is a circumscribed circle. So it is being or enclosing a given triangle inside itself. So we are going to see how we can construct another one. and that one we do describe it as inscribed circle. Let's see how we do construct. In construction of inscribed circles, together you may be issued with some measurement of given sides of a triangle, or you may be given a triangle drawn and you will be asked to construct a circle which will be on external parts of or produced parts of some sides of that triangle. So the circle will be touching the sides of the produced and one of the side which is on the triangle. So let's see how we do construct that. I shall start with one of my triangle here. Having this triangle here as A, B, C is my triangle. What will you do if you have a triangle like that? You produce the sides AC such that it will be AC produced, and producing means you extend that side outside. You extend that way. That is what we refer to as producing a given side. The same applies to side AB in case if this is the place where we need to draw that. So we shall produce that side AB such that we have that given side. So the given there is AB produced and this one here is AC produced, as you can see. So from there, use your pair of compass. Now, if you need to construct a inscribed circle, you will open any radius. You bisect an angle which we may refer to this point. Let this one be as T and this one Q. So we are going to construct angle, we are going to bisect angle TBC produced, which is outside there, or ABC produced. So if we are going to construct angle ABC produced is this angle here, or angle TBC. So we are going to bisect that angle, and opening a radius, we shall cut line AB produced and line CB using the same radius, and then we use that axe to construct or to make axe at the center to construct that given line. So if that is the case, we shall join where the two lines intersect with the angle. The two axes intersect at that point, and the angle, we join them together, we draw a line. So that is what we shall have. You may call that line as L1 or leave it that way. Then after that, we are going to construct angle ACB produced or angle QC. So on constructing it, we shall have, I will open any radius and I bisect this angle here. And then using any radius again, I bisect, I draw two axes at that center, so we shall have that one. Then I join the point where the two axes meet with the angle, the produced angle, so we shall have, I'm going to have that line there. That one is bisecting this angle ABC produced or angle QCB for our case. So if that is the case, having the center as the point where the two bisects intersect, we are going to draw a circle which touches the side AC produced and AB produced and CB, or side CQ, BT and CB. So we shall have that one as the center. Then you draw a circle which touches the sides. Let's see how it looks like. For my part here, I'm finding that the triangle which I drew, having the center as, let's say this one as O, this center O, I'm having that circle which I have drawn touching line CB at this point here, as we can see, and also we have a space here, then touches the lower part at this point, and also at that point there. So it touches the three sides, I mean, that is AB produced at this point here, and CB at the point here, and also AC produced at point there. So we are having that circle there. So this circle is what we are referring to as inscribed circle. And here, where we have that center is known as X center. So with that, we have seen how we can construct given circles from given triangles and the rules which guide them. That is how we do construct them. So next we shall be looking at triangles, and that will be orthocenter and centroid. We have seen different kinds of centers in a triangle which we use to construct circles. Now we are going to see other centers of a triangle, and we shall be looking at orthocenter and centroid. For that instance, we are going to start with the orthocenter, and we shall start with a triangle, given a triangle like this. If you have a triangle of that kind, such that this may be A, this one here B, and this one C, we can construct our orthocenter by constructing the medians of each side. So if we construct the median here, you will seek where the median of line BC is located, and you may find the median is at this point. Then you make sure that you connect the median there, or the midpoint of that side to A, so that to that angle there. And also you find the median of the other one down here, so you find that it is almost there. So on finding that, we are going to have, so you will have your triangle cutting or having medians. This point here is the median of line AB. This here is the median or the midpoint of AC, as this point here is the midpoint of BC. If you have a triangle whose midpoints, or the lines joining to midpoints of each side and the angle, opposite angle, intersect at this point, that is what we usually call an orthocenter. So this is what is referred to as orthocenter. This is orthocenter. That is what we call orthocenter. So we are going to see another case where we are having a centroid. We have said this one is for midpoint. Now for a centroid, we drop altitudes. For example, we may have another triangle. Let's see. That's my triangle ABC. I need to construct a centroid, and in order to construct a centroid, you need to drop altitudes to any of the sides, such that the point where the three altitudes intersect is what we refer to as a centroid. So altitude of this line here, BC, B actually will be dropped by, if you are at C, you drop a perpendicular bisector of line. You drop a perpendicular bisector of line BC, such that you will have, you cut that line at that point and also at this point. If you drop a perpendicular, you will now be required to open any point here, construct here an arc, and also at down here another one. Stand at the other arc, construct at the top, and also at the bottom part. So that you now pass the given line through that, and you will find it will pass through that given angle. So it will be in this kind. It is passing through that given angle, and this angle here is 90 degrees, as you can see. So that is how you shall drop that. And then if you want to drop another one, or to construct an altitude of line CB, then you need to open your radius, cut the line, open any radius, cut that line having, so you will cut having that radius, you will cut that line at that point, and then after cutting, you will stand at the arcs which you cut on that side, construct a perpendicular Then the same applies to the top with the same radius. After that, draw a line passing through the arcs and the angle here. You will find that that line will pass through that and that angle, and if you measure this angle, you will find it is 90 degrees on both sides. The same applies to the other side. You construct an altitude, and an altitude is just dropping a perpendicular from a point, so it means you will stand here, drop a given perpendicular to line AC with any radius, drop a perpendicular to line AC. So you need to bisect that line, maybe at that point. Then with any radius, construct a perpendicular that way. Then after constructing that perpendicular and that two bisectors which you used as a perpendicular at that point, join the point where they intersect with the angle. So you will find out that they all passes through point B. So we have a convenience here. So you will find out that after constructing, the lines intersect at this point here, but the angle here is 90 degrees or perpendicular to the sides. Remember, you draw a perpendicular from a given point to that line, and then you construct a perpendicular passing through that angle of any given angle on the side. And that one, after dropping or constructing an altitude to each given side, you will find out that the center which you will form is what we refer to as a centroid. The other one was orthocenter, this one is a centroid. With that, we have come to an end of circles, chords, and tangent, form 3 topic 7, and I would like you to subscribe to our channel for more videos.